see in nature that many atoms will be able to take a different number of neutrons. And unfortunately, there's not a very easy way to predict how many neutrons a particular atom is stable with. For example, chlorine here comes in two what are called isotopes, chlorine 35 and chlorine 37. These are called isotopes. And they vary only by the number of protons. I'm sorry, by neutrons. Of course, if it were protons, they would be different elements. So they vary by the various number of neutrons they have. And we'll see that the convention for naming these isotopes is using something called a mass number. These two numbers here are mass numbers. And mass numbers are always whole numbers. The mass number is equal to the number of protons plus the number of neutrons. It's where all the mass is in the atom, right? We have protons which have mass, neutrons which have mass, electrons, again, so insignificant we don't really worry about them. So your mass number is your number of protons plus neutrons. And this is therefore always going to be a whole number because we can't have half a proton or something like that. Half a neutron doesn't exist. So mass numbers are always whole numbers. But if we look right below those isotopes, I've written their actual masses, their isotopic mass, the mass of that isotope. So while chlorine 35 has a mass number of 35, its mass is actually 34.969 AMU. And that's again just because of the slight differences in protons and neutrons. They don't weigh exactly 1 AMU, they're approximately. And as you can see, that number is very close to 35. And then for chlorine 37, again, we're very close to 37. So we kind of we can get away with referring to things by mass numbers. However, if you look on the periodic table, we see that if we look at chlorine, we'll see that we actually have this number 35.45 AMU under it. And if we go ahead and see, everything else, we see 17 and CL, that's normal. This 35.45 doesn't seem to match with any of the numbers we have. It turns out that this number down here is not the mass number, of course, because mass number is always a integer. There's no decimals with a mass number. This is what's called the atomic mass, which is a weighted average of all isotopes. Stable isotopes, we should say. We're going to see that let's try again. Isotopes. There we go. When we have isotopes, there are ones that are unstable. We can make them in a laboratory, for example. Or there may be ones that are just radioactive by nature. And so we really are only concerned with the stable isotopes here, which mean they're not radioactive, they don't decay. And so when we think about a weighted average, we'll see that the atomic mass is equal to the sum of the isotope mass. One day I'll learn how to spell isotope on the first try, but that's not today. The isotope mass times the relative abundance. So in nature, we're going to see that certain isotopes are more common than others. For example, with the chlorine, the 35 chlorine isotope is about 75% of all chlorines will be that isotope. And about 24% will be chlorine 37. And as you can see, those two numbers add up to 100%. We don't really see any other stable isotopes of chlorine. So chlorine 36, for example, doesn't exist, which is interesting. We typically don't see things with odd numbers of neutrons. That's just kind of one thing that we see here. Since chlorine has an odd atomic number, these mass numbers both indicate an even number of neutrons, right? one with 18 neutrons, the other one with 20 neutrons. For whatever reason, odd numbers of neutrons are less common in stable isotopes. Again, it's not a rule of thumb, it's just a generalization. There are absolutely exceptions, many of them. But generally speaking, usually odd numbers of neutrons are not very common in stable isotopes. But we don't need to worry about that. We don't need to know why ones are more stable than others. That's something for next semester when we study nuclear chemistry. But for right now, we just need to worry about this abundance and the isotope mass. And so it's somewhat of a trivial exercise, but we can do it. If we wanted to figure out where this atomic mass came from, we would just need to add up the products of the isotope mass and their abundance. So for this chlorine business, let me just copy these numbers here. And we can see how to do the math here. We'll see that we want to do the product for each isotope. In this case, there are 2 isotopes. Some elements have 8 stable isotopes. Some have just 1. Some have 20. Some have 3. There's no real rhyme or reason. Hydrogen has 3, for example. Carbon has 3 as well. Helium, I think, just has 2. So who knows? So when we look at these, we want to use the isotope mass and the relative abundance. So for chlorine 35, that's 34.969 times the percentage in decimal form. Since this is a summation, that's what the sigma means there. The capital sigma means we're adding together all the products for all the isotopes. 36.966 times 0.2422. Bust out thy calculator. I have lost mine. No, it is right here. Okay, let's go ahead and do it. 34.969 times 0.7578 plus 36.966 times 0.2422. Lo and behold, we get 35.45. 26 if we really wanted, but we know we have 4 safe based on these what are they called? Percentages, the abundance. Unit for this would be AMU, because that's the units we had to begin with. And notice that's indeed the number we see underneath chlorine on the periodic table. So that's how atomic mass is calculated. It's the weighted average of all stable isotopes. And we'll see next chapter how we can actually use this in talking about weighing out atoms and how many atoms there are in that sample or in a molecule or whatever it may be. So, in summary of this section, isotopes arise when the same type of atom, chlorine atoms in this case, have different numbers of neutrons. Different atoms, different elements, have different numbers of stable isotopes, and those all go together with their abundance and their isotope mass in calculating the atomic mass, which is that third number we see on the periodic table for all of these. In our next video, we'll just take a look at some general periodic trends in identifying sections of the periodic table.